Evening. I'm spot on weather meteorologist Matthew Euler. Welcome to my latest video here. Now, I know it's been a little bit of time again since my last video. I tell you what, I've been working on writing forecasting guides over the course of the summer, and I put those on my weather website on Spot on Weather Weebly. If you go to the forecasting guides tab, you can see what I've been working on really since late spring and over the course of the summer so far. So I've really been occupied with doing more detailed write-ups and guides. Not really been doing many videos, as you can tell from the output here on the YouTube channel. But I'll get back into the swing of things as we get closer to the fall, as far as more frequent videos. But as of right now, I'm into a lot of writing and just sharing the weather knowledge that way. So I wanted to do a special video. This one's really interesting. It's so hot and humid right now. We're sitting here almost in mid-July. And I wanted to do a special video, kind of think a little bit cooler thoughts here. And this video is called The Changing Polar Jet Stream During Arctic Amplification. And I'm going to get into the details of this as we go through this presentation. Let me go ahead and get my laser pointer ready to go. All right, so on the title slide here, you see the orange coloring here. This is the outline of the polar jet stream, just kind of showing you where the strongest winds with the darkest orange colors are associated with the polar jet stream. So a little bit of troughing this on this title slide off the Northeast Pacific, ridging over the western portion into the northern plains of the U.S., and then troughing again right on into the New England area. But I wanted to really talk about the characteristics of this wavy river of air in the upper atmosphere, the jet stream. So let's get right into it. The overview of the video here this evening is I'm going to go over the references first, kind of like what I looked at and researched, previous work that's already out there. Then we'll dive into the polar jet stream defined. We'll define that. The polar jet stream characteristics as well as its importance. And then we'll look at the Arctic amplification and define that. Moving on then to Arctic amplification and a changing polar jet stream. We'll talk about what potentially could be happening due to this Arctic warming. And then I'll throw some past weather examples in there. And then finally, I'll conclude with findings. And here are the references I utilized, putting these slides together. This is previous research already out there. All you got to do is, go and Google these topics. The first one is shifting winds, how a wavy or polar jet stream causes extreme weather events, from Dr. Francis in 2024. This was pretty recent, actually. The polar jet stream, the polar vortex by Kang and Kroll. That was done back in 2024, pretty recent as well. Then we have the study on the winter jet stream and how it was erratic before climate change. That was done by Chalif, Gerini, and Oosterberg back earlier this year, actually, in 2025. And then also I looked at the influence of high latitude blocking in the northern stratospheric polar vortex on cold air outbreaks under Arctic amplification of global warming. And that was done by Edward Hanna and et al., 2024, in the Environmental Climate Journal there. And then Arctic Hotspots study reveals areas of climate stress in North Alaska and Siberia. That was a research study conducted by Watts et al., 2025, in the Geophysical Research Letters. And then finally, I took a good look at the NOAA 2024 Arctic Report Card. So let's first define what the polar jet stream actually is. Let's define it. And I took this right from the American Meteorological Society definition or glossary list. The polar jet stream is a strong west-to-east flowing river of air in the upper atmosphere that separates the cold polar air to the north from warmer mid-latitude air to the south. That's all it is. The jet stream, again, showing another graphic here on the bottom right. Again, the orange colors and the yellow colors really outline the polar jet stream in this example. Now, we do have these troughs and we have these ridges that are associated with the polar jet stream. And there's different weather associated with these ridges and these troughs. And we'll get more into that here shortly. But in general, just think of the polar jet stream as that river of air in the upper atmosphere. It generally occurs at 30,000 feet in the winter, 40,000 feet in the summer season. And north of this jet axis, you have cooler air, and south of this jet axis, you have warmer air. All right, so let's look at the polar jet stream characteristics now. It's generally found in the upper troposphere. I put around 30,000 feet or 9,100 meters above sea level, but this does change seasonally. The polar jet stream is around 30,000 feet in the winter season, and it goes up as high as 40,000 feet or the 200 millibar level in the summer season. Now, the jet stream forms along the boundary where you get these cold air masses from the Arctic meeting warmer air masses from the middle latitudes, and it does not flow in a straight line. A lot of times you're going to see the curvy nature of the polar jet stream. It's not going to just flow, in a straight line. It tends to meander in this wave-like pattern, creating dips as well as those ridges that can extend far south and as well as far to the north with the ridges in the middle latitudes. Again, colder air is located to the north of the polar jet stream with warmer air to the south. So some diagrams here on the bottom right. We'll start with this one here where my little red laser pointer is. This showing you an example of the polar jet stream, where you see the upside down U shape with the warmer air beneath it. That's associated with upper ridges. Where you see this dip in the jet stream, that's known as an upper trough, and you can see the colder air generally is going to dive into the troughs. The warmer air moves to the north in the ridges. And over here on the bottom right, far bottom right, we're just showing an example of the polar jet stream and where it generally forms. Generally, it forms because you get milder temperate air from the middle latitudes converging with these polar air and Arctic air from the Arctic region, right there along the polar front at 60 degrees north latitude, high above these surface storms at 60 degrees north latitude along the polar front. You got upper level, stronger jet stream winds, and that is associated with the polar jet stream. Further south, 30 degrees north latitude, you generally have a subtropical jet stream. Again, these type of upper level winds, upper level rivers of air, they tend to form, where you have competing influences from various cells. The polar cell, the mid-latitude or Ferrel cell, and the Hadley cell. All right. Additionally, with the polar jet stream, warmer air is associated within the ridges, colder air is associated within the troughs. And the big thing about the polar jet stream, it does act as a steering current for weather systems. So you get these, what do we call, baroclinic lows and baroclinic highs are steered by these upper level winds. It generally will indicate the storm track, for example, where the axis of the polar jet stream is located. And its position and strength can significantly influence the severity as well as the frequency of weather events in a region. Again, with the polar jet stream, just think about this. It's stronger in winter, which when I say the jet is stronger, I'm saying it has higher wind speeds due to larger temperature differences between the poles and the equator in the wintertime. It is weaker in the summer season, which means slower wind speeds in summer because that larger temperature gradient is not there anymore between the poles and the equator. It does tend to shift northward, the polar jet, in the summer, closer to the United States-Canadian border, and it can move much further south into the United States and across Europe, mid-latitudes in general in the winter season. All right, so now let's just examine some graphics here to kind of really hone in on the characteristics of the polar jet stream. All right, so notice in this example here on the left, this red solid line represents your polar jet stream in this example. And you'll notice where you see these dips form the shape of the letter U, looks like the letter, basically forming a letter U here. These are called troughs where the jet stream dips down into the mid latitudes. You get stormy weather with those. And when you see the upside down U shape, that's known as a ridge associated with upper level higher heights or upper level high pressure and sinking air motion and dry weather. Over here on the right side, we're showing generally the blue color here indicates generally the most favorable location in relation to the polar jet stream where you'll see the most stormy weather. And that's generally going to be on the downstream side of the trough. So if you have a trough axis right down the center of this jet stream shape, this U, the letter U shape in the trough, you get a jet axis, a trough axis, excuse me, generally downstream of that trough axis. And this blue oval area is where typically storms develop across the mid-latitudes. Generally, if you're in this upside down U shape underneath that, the ridge pattern, you're generally going to be abnormally warm and dry. All right, so it's important, the role that the polar jet stream plays is rather important as far as the placement of where the stormy weather is, as well as the dry weather, the placement of where the coldest temperatures are located and the mildest or warmest temperatures are located. So it really does matter for you to pay attention to where this polar jet stream is located. Again, this blue oval shape here on the right, that if you're anywhere, let's say in this example from New Mexico, New Mexico, Colorado, and Nebraska, you're probably going to get more storminess in this example. All right, additionally, within the polar jet stream itself, we have these accelerated areas of wind speed known as jet streaks, and these are faster winds within the polar jet stream core, the jet streaks. They're important in that they promote either rising stormy conditions or sinking fair weather, depending on your location in reference to these jet streaks. All right, so if you look at the left here, we're showing just a west to east straight jet streak. Okay, so at the center of the jet streaks are the strongest winds, in this case 110 knots, and the deep blue color here, the deeper blue color here. And it's generally oriented from west to east. So generally what you have to the left of the jet streak in a straight, in a polar jet stream that is straight, the jet streak that is straight, you get more of the upper level, these areas, quadrants in relation to the jet streak. The left front is known as the left exit region, where you get upward vertical air motion over here. And then the right rear quadrant of the jet streak also is favorable for upward or rising vertical air motion. So that's generally when you have rising air motion in the atmosphere, you're going to get more in the way of clouds and most likely precipitation. Let me go ahead and draw this out for you as I explain it so you kind of get an idea. So to the left front or the left exit region, oh, I don't want to do that. You're going, I did it again. I'm going to draw the up arrow here. Okay, that indicates rising upward air motion, and most likely your storms and cloud in the left front or left exit portion of the jet streak in a straight jet streak. And then also you're going to have the same thing. I keep doing it. I apologize. I'm trying to draw it out. I promise. All right. I'm getting used to a new laptop here and the functionality of the buttons. So as you can see, I have an up arrow here. Okay. So those are your two areas, the left exit and the right entrance regions of the jet streak, or the way I learned it was left front quadrant and the right rear quadrant. Now, what happens over here in the left entrance region of the jet streak, you're generally going to have, let me do this here, sinking air motion. Oh my goodness, I apologize here. I'm gonna have to learn how to do this. Oh, now it just erased it. Okay. Anyway, you get downward vertical motion here. Oh my goodness. All right, and then you also get downward vertical motion at this location here. Okay, so you got it there, and you got it here. All right, it's going to drive me nuts because I'm learning this mouse pad here. But in general, when you get downward vertical air motion at this location here, and at this quadrant back here, right in here is downward vertical motion, downward motion. You're generally going to get fair weather when the air is sinking in the atmosphere. In the right exit region over here, let me do this again, right exit, downward motion. All right. That's a straightly oriented jet streak. Now, what happens if we have curvature to the jet streak? You still generally get this left exit region right in here. Okay, that's going to promote rising air motion. I know, I think I figured it out now. All right, so thank you for being patient. I tell you what, learning this technology sometimes can get you. But all right, so the left exit region in a curved jet streak, you get rising upper vertical motion in the left exit region, clouds and storminess. And then the left entrance region of the jet streak in a curved jet streak, you get downward vertical motion and more fair weather. So jet streaks, again, they're very important. Wherever you are located in relation to these jet streaks really matters, especially when you get into the fall and the winter season specifically. All right, so now let's move into a discussion of Arctic amplification, what exactly this is. Arctic amplification is basically the phenomenon where the Arctic region is warming at a rate 2 to 4 times faster than the global average. So, yes, we're seeing warming temperatures associated with the Earth. The data supports that. But the Arctic is warming at a rate twice to 4 times faster than the global average. The Arctic is experiencing a greater temperature increase compared to the rest of the planet. Sea ice melts and reduced albedo. And albedo is just simply reflectivity. This drives Arctic amplification through a positive feedback loop. So you don't have the sea ice, it's declining, right? You got sea ice melting, you got a dark water surface, you're reducing your reflectivity because ice is a good reflector of incoming solar radiation. And so you're warming the water, and in effect, it's warming the overlying atmosphere, which is further driving warming temperatures, which is basically known as Arctic amplification. Additionally, you're getting increasing amounts of moisture that's flowing into the Arctic region. Now, with increased water vapor, that moisture in the atmosphere, this is going to occur due to warmer temperatures and increased evaporation. Well, if you have the ice melting, then we have open water, more open water in the Arctic, and that's going to lead to more of an increase in warming the temperatures and increasing evaporation from that water surface. Remember that water vapor, if you increase that water vapor, it is a greenhouse gas, which traps heat and further contributes to warming. Now, changes in atmospheric circulation, Arctic amplification can affect global wind patterns, including the polar jet stream, potentially leading to more extreme events across the middle latitudes. One other thing I found really interesting is this permafrost thaw. As temperatures rise, this permafrost, the permanently frozen ground in the Arctic, as it thaws out, it releases greenhouse gases such as methane and carbon dioxide, which is just further accelerating the warming of the Arctic. So you kind of see, we call this a positive feedback loop. One thing contributes to another thing, and that thing then contributes to another thing, and it continues on and on. All right, so with the Arctic warming fastest compared to the rest of the planet, the temperature gradient between the poles and the mid-latitude becomes less. Okay, this weakens, that lessened temperature gradient is going to weaken or slow the wind speeds down the polar jet stream, allowing it to bend in a more wavier meridional pattern. And the jet stream becomes more unstable when these wind speeds within the jet slow down. Arctic air will then plunge further south into these troughs within the polar jet stream, into the middle latitudes, while unseasonably warm air moves north in these ridges, these upper ridges associated with the polar jet stream across the Arctic. Extended periods of anomalous weather may then result with the deeper troughs and stronger ridges setting up. This does not allow for high and low pressure systems to move quickly through an area when you have this wavy pattern. Instead, these pressure systems stall out, resulting in drought, intense storms, and significant temperature anomalies. Over here in the bottom right, I got this is from Paul Horn, Inside Climate News, Paul Horn. The source is NOAA and Scientific American. And this really breaks down, okay, how does Arctic warming affect the jet stream? The difference in temperatures between the Arctic and the areas further south, that temperature difference, when it's stronger, the jet stream, the polar jet stream, tends to basically blow from west to east. There's less waviness to it. A stronger temperature gradient across the latitudes allows the jet stream to be stronger, those wind speeds within the jet. However, if you get the warmer Arctic, that reduces that temperature difference, as I mentioned, which weakens the winds within the jet and favors a wavier flow. So you get bigger waves moving slowly and allowing warm air to stream northward into these ridges, while cold air dips southward into these troughs. So here's the examples again. Look at this diagram. These arrows represent the polar jet stream axis, pretty much blowing from west to east. It's very strong jet stream, cold air to the north, over the Arctic, warm air to the south across the mid-latitudes. And this is when you have a large temperature difference across the latitudes, from the tropics to the poles. But what happens over here in the bottom right is you see how the jet stream is now, this polar jet stream has more amplified ridges and deeper troughs. So when the jet stream then weakens, it becomes wobblier, allowing cold Arctic air to move southward. It gets displaced off the North Pole area. So with a warming Arctic, now this data is strictly from the 2024 Arctic report card now. Over here on the left, I'm showing an example of a city located in the Arctic, Barrow, Alaska. And if you notice on this graph here, this chart, the blue areas, okay, first of all, we're going back to 1920. We're going 1920 to 2010. And if you notice, this red line just generally represents your 5-year average. So you kind of see the temperature, 5-year temperature average kind of going up and down, up and down. And then you'll notice over here in the far right portion of this diagram how that red line just accelerates up, right? The temperature is in degrees Fahrenheit here on the y-axis, this vertical axis over here on the left. So you can just see how Barrow, Alaska is drastically warming. I mean, especially from about 1996 to present time, it is really warming. Again, the monthly average is in blue, by the way. So it shows the red line in respect to this monthly average of the blue line. So you just see this spike or acceleration in the 5-year average of warming temperatures for Barrow, Alaska. Now this is for October. This is October temperatures. All right, I just chose to pick a month to kind of show you this. Now the most substantial warming occurs in far eastern Siberia, tundra through central Siberia, and it occurred between 1997 and 2020. So this graphic here on the bottom right shows warming severity. And you see the darker the brown color, the more severe or extreme the warming. And you kind of see where the warming is the strongest here across Siberia. 99% of Eurasian tundra experiences significant warming. Now, this is from research conducted by Watts and et al. But you generally see this deeper brown color on the Siberian side of things, Eurasian side of things. Again, one thing to mention here, melting permafrost, that frozen ground melting, and increasing wildfires across this area increases carbon emissions. The Arctic, by the way, has been a carbon sink for thousands of years, storing more carbon, but now it's beginning to release this carbon into the atmosphere, which acts to further warm the Arctic. This graphic here shows the 2024 Arctic surface temperatures, which, by the way, were the second warmest on record. And I mean, look at all these deeper orange colors, kind of like in the deeper areas here in the Arctic. So you really see this dashed white line represents the Arctic Circle. Okay, so north of 66.5 degrees north latitude. The time period here is October 2023 to September 2024 versus average. Now they're using average from the 1991 to 2020. The data is the C3S Era 5 data. So anywhere you see these deeper orange colors, these deeper tones, that indicates very quick warming. And you see it right here, the scale underneath it, just kind of showing you up to 8 degrees Fahrenheit, 4.4 degrees Celsius in the darkest areas. Yearly temperature since 1900. Now this compares, this graphic on the bottom, is going from 1900 to 2024. And notice the red line here on the bottom graphic represents the Arctic, and look at the acceleration, specifically since 2000. The Arctic is warming faster than the global average, all right? And so you see what's going on here recently. The Arctic is really, really I know you see a little bit of a dip back down and then kind of a rise and a dip and back up again. But really, you can clearly see how things are changing across the Arctic as far as temperatures go. Again, Arctic annual temperature in 2024 ranked second warmest since 1900, and the last 9 years are the 9 warmest years on record in the Arctic. Just phenomenal. In addition to the warmth, when you have warmer air, it can hold more moisture. So you're getting a wetter Arctic. You're getting a wetter Arctic as temps warm. So we're not only getting warmer air into the Arctic, we're getting moisture air into the Arctic. And you'll see here, this is a rank of the highest 5-day precipitation here on the left. And you see the darker blue areas in the Arctic represent the wettest, highest 5-day precipitations. Now, this was from January to March of 2024. Okay. But you see the darker blues here indicate very, very wet, high ranking wetness across the Arctic. Look over here on the bottom, Arctic winter precip is increasing over time. In fact, some of the areas are actually getting above average snowfall across the Arctic, but that's because the air temperatures are warming. And again, with warmer air temperatures in the Arctic, it can hold more moisture. And so, despite the warming temperatures, you're getting more cases of above average snowfall in many of the Arctic areas, but you're also starting to get more in the way of mixing and freezing precipitation events, sleet, freezing rain in places across the Arctic that pretty much always had snow in the past. Okay, so summer 2024, by the way, was the wettest on record across the Arctic. That was last summer. Additionally, when we talk about the warming Arctic, we have to talk about the sea ice. Now, this was September 2024 sea ice. Now, you see the different lines on this graph on the left, this diagram. So the white line represents where the ice was, the extent of the ice was in Septembers of the past. All right, so we're looking at Septembers from 1979 to 2024 here. And the white line on this graph here, or this diagram here, display, indicates where the ice was 1991 to 2020. And then this kind of like an orangish line here, I guess you'd call it yellow if you want to. This shows the average extent of the sea ice across the Arctic from 1981 to 2010. So you see the differences here. In 1981 to 2010, the Arctic sea ice was much further towards areas such as Barrow, right? Closer to some of these Arctic land masses. And now it's becoming less and less in aerial coverage, the Arctic sea ice in Septembers. Down here at the bottom, I'm showing you the summer minimum sea ice extent, again, from 1979 to 2024. And you just see in September how the decline has continued, with this dashed line being the trend line and the solid blue line being observations. So just some facts here on the right. In September 2024, the extent of Arctic sea ice was the sixth lowest in the 45-year satellite record. Now, if we're looking back to the satellite record, we're looking back to about 1979. But all 18 of the lowest September minimum ice extents have occurred in the last 18 years. I mean, talk about consistency for the lowest September minimum ice extent. The Arctic Ocean regions that were ice-free in August have been warming at a rate of 0.5 degrees Fahrenheit per decade since 1982. Just impressive. All right, so now kind of getting back, kind of showing you from the Arctic report card what's been going on in the Arctic. Let's now examine this discussion again on the weakening polar jet stream potentially. And over here on the right, I'll also talk a little bit about the stratospheric polar vortex, because that definitely helps to shape the tropospheric polar jet stream. So over here on the left, let's start over here. With the weakening polar jet stream again, when we talk about temperature differences becoming less across the latitudes, that also leads to lesser pressure differences between the cold air in the Arctic and warm air in the mid-latitude. So again, that's the relationship between the temperature and the pressure. If you decrease the temperature gradient across the latitudes from the tropics to the poles, you also decrease the pressure. And this natural barrier keeps the freezing temperatures of the Arctic winter from intruding further south. Okay? That's usually the role of the polar jet stream. It keeps the coldest air locked up over the Arctic. So when the polar jet stream is strong, as we're showing here on the left, powered by larger temperature differences between the Arctic and the mid-latitudes, it moves relatively straight west to east. This keeps the coldest winter temperatures in this predictable ring, this white arrowed ring, the Arctic environments of Alaska, northern Canada, Greenland, Siberia, and Scandinavia is where the coldest air resides in the winter season. But if we warm the Arctic, it produces a weaker jet stream, and that jet stream is represented by these solid white line, the solid white line with the arrows. So if you're getting a weaker jet stream with the Arctic warming, it's more likely to bend off course. And this wavy pattern can shift the boundary between the cold Arctic air and the warm middle latitude air to strange, very unusual places. Southerly regions used to seeing milder winters may be exposed to freezing temperatures at the same time that parts of the Arctic deal with unusually warm spells. So unusually warm in the Arctic and unusually cold and frigid further south, the places that normally don't see that kind of frigid temperatures. And we saw this just last year with the major Gulf Coast snowstorm, the winter of 24-25. We saw it back in January of 25, where very cold air went all the way down to the northern Gulf of America. And yeah, I mean, we had some record snowfalls from Louisiana to Florida in this case. Now, I would be remiss if I don't mention about the stratospheric polar vortex here. It does play a role. It connects to the polar jet stream. So generally, these circular areas that I'm showing here on the right, you generally have a more stable polar vortex in this case with a stronger polar jet stream. So I just want you to think of that. A stronger stratospheric polar vortex will tend to keep all the coldest air locked up over the Arctic, and it leads to this concentric ring where the coldest temperatures remain over the Arctic. That's with a stronger, stable polar vortex in the stratosphere. However, there's cases where this polar vortex in the stratosphere can be displaced. That cold low pressure core can slip off the pole and travel further south into the middle latitudes. And then also the stratospheric polar vortex can do what we call a split. The polar vortex breaks into 2 or 3 pieces with low pressure areas forming in multiple places far from the pole. And we've seen this quite a bit where the polar vortex, it does not seem to be strong throughout the entire course of the winter. And many of the past winters we've seen recently, at some point in time, we get a weakened polar vortex in the stratosphere, whether it be a stretching event or even a splitting vortex. But just think about this. The weaker the stratospheric polar vortex, the wavier and weaker the polar jet stream. The stronger and more stable the stratospheric polar vortex, the stronger the west to east jet stream, the coldest air remains up over the Arctic. Here's an example that I took from one of the charts, the 500 millibar charts that I saved in the past. Now, this chart was back from the 20th of December of 2022. This, if you recall, was right before the major just Arctic frigid blast went all the way down into the Midwest, the East Coast, New England, the Deep South got in on it too. Just a frigid drop off in temperatures. I remember being here in the Mid-Atlantic in Virginia, and I was like, "Wow, this is a heck of a shock to the system." But what I want you to pay attention to, these green colors represent a lower than normal atmospheric heights at 18,000 feet in the atmosphere associated with colder temperatures. Where you see the greens and these purples, that indicates lower than normal atmospheric heights at 18,000 feet and colder than normal temperatures. Where you see the browns or the light whites, these areas here indicate anomalously higher than normal upper heights at 18,000 feet, which is associated with ridges. Basically, this is more of a wavier jet stream. You see this huge ridge expanding northward into the Arctic regions, actually on both sides, the North Atlantic side over here in the Greenland, and then also into the Bering Sea and the Pacific side over here, Beaufort Sea, Bering Sea area. So this is kind of like what a 500 millibar chart would look like, okay, prior to a major Arctic outbreak, cold air outbreak coming down to the U.S. You get unusual warming up into the Arctic regions with these upper ridges, and that helps to displace very frigid cold Arctic air southward into the United States in this example. So yeah, this was just prior to that extremely cold air outbreak in the U.S., just prior to Christmas in 2022. If you look over here on the right, I'm showing some examples of what a wavy jet stream, polar jet stream looks like. You get these low pressure areas, these blue bubbles. The white L represents low pressure in the troughs of the jet stream. And then you get these red bubbles. The white H indicates upper level higher heights or upper level high pressure. And that's associated with a warmer, very dry weather. It can be record warmth in some cases when you get this kind of strength of a ridge. And then in the troughs, it's much colder and stormier. But you notice the purple line here, this represents the flow of the entire polar jet stream. And so there are some cases where you get this Rossby wave breaking to occur. And when the Rossby waves break, they sometimes can work their way from the troposphere where we live up into the second layer of the atmosphere, the stratosphere, and actually disturb the stratospheric polar vortex. So just wanted to show you what a wavier jet stream would look like. Again, the troughs, stormy and cold, the ridges, unusually mild and dry. So we keep looking at the stratospheric polar vortex and the polar jet stream changes. A strong stratospheric polar vortex, SPV, helps contain the cold air at its core over the Arctic. If the SPV, the stratospheric polar vortex, is disturbed, it can slip off the North Pole or even break up into those multiple pieces, those vortices. This is an example of I'll show you this here in a minute, but let me just continue on with the words. So in January and February 2019, the stratospheric polar vortex, the SPV, it weakened, leading to extreme winter storms and broke cold temperature records across the eastern U.S. and Canada. And that was just one example. I got other examples I'll show you here in a moment. But in general, I'm showing you some graphics here. Now, the source of these graphics is from Matthew Barlow. Okay, so that's where I pulled it from Matthew Barlow. But in general, what you have in this case is you get these. I talked about these Rossby waves on this slide, right? Over here, right here, where my red little laser pointer is. Rossby wave breaking, where sometimes the energy from these Rossby waves can break up into the stratosphere. And when that happens, in this case, I'm showing you this diagram here on the left at the bottom, or the center bottom. You see these red arrows indicating that wave energy kind of going up towards the stratosphere. And what it does, this wave energy can actually weaken the stratospheric polar vortex, right? And so in this case, we have a stretched stratospheric polar vortex. That the vortex shape is represented by this black solid line, okay? So the wave energy propagating, these Rossby waves breaking into the stratosphere, reflecting off the stratosphere itself, but resulting in a stretching of the stratospheric polar vortex. And then the energy works its way back down towards the surface over North America. So energy up over Eurasia, reflecting off the stratosphere, stretching out the stratospheric polar vortex, and that energy then works its way back down to the surface in North America. This happened a lot last winter, a lot. And we had very cold temperature periods across the eastern U.S. as a result of this process, this stretching of the stratospheric polar vortex. Dr. Judah Cohen, who's done a lot of research on this, he talks about, the position of this wavy jet stream, the specific part of it, the upper ridge portion of the wavy jet stream over the Ural mountain areas. Okay. That's over Eurasia. It tends to reflect off the energy reflects off the stratospheric layer and then works its way back down and brings colder air to the eastern portion of the U.S., east of the Rockies. Now, over here, the last two diagrams at the bottom right here, I'm showing you an example. This purple line represents the shape of your stratospheric polar vortex. When it's strong, it's more symmetrical or circular in shape. When it's stretched out, the stratospheric polar vortex, it becomes more elongated like a rubber band. See this? See the differences in shape between a strong, stable stratospheric polar vortex here on the left and then a unstable and weakened stratospheric polar vortex on the right. The shape of this is much different. Additionally, this is from Matthew Barlow as well, University of Massachusetts, Lowell. Look at this. This is a stratospheric polar vortex and how it impacts the polar jet stream configuration, okay? So initially, and by the way, you can see we're going from October through February. That's the focus time period here, okay? So the Arctic climate is changing. It's warming, right? It's forcing upward wave activity from the troposphere towards the stratosphere, which then leads to that stretched stratospheric polar vortex, which sets up what's known as wave reflection. The energy goes up over Eurasia, bounces off the stratosphere, comes back down over North America, and it changes the shape of the stratospheric polar vortex. This middle diagram here, I have my red little laser pointer on. The black solid line is the shape of your stratospheric polar vortex. So you notice how it's becoming more elongated in shape. And then this is a result. Look at this. This leads to a southward shifted polar jet stream over North America, and this blue color indicates below normal, colder than normal temperatures east of the Rockies. And you have a lot more warming up over the Arctic region in general. Okay, so it kind of shows you how we have warming, we have upper level ridging setting up over the Ural Mountain area, the Ural area of Eurasia in October, and by December, that energy is reflected off the stratosphere back down towards eastern North America, and voila! Look at this blue solid dashed line is your jet stream axis. By the way, this is where your polar jet streams is. And look at this. Look at this. Much colder temperatures by January and February, late in the winter season, over the eastern U.S. All right, so now let's move into the recent cold weather outbreaks and this weakened or wavier polar jet stream. Now, I just went back to 2010. I just went back 15 years to see how frequent this is occurring, this wavier weakened polar jet stream in the winter season. We'll start with January 2010. Now, that 09-10 winter was very special in the fact that we saw an extremely negative Arctic oscillation as well as an extremely negative North Atlantic oscillation. February 2010, kind of continuing on that winter, we saw cold and record-breaking snow for many locations from the mid-Atlantic up to New England in the eastern U.S. February 2015, another example where we had a weakened polar jet stream. We saw more of a milder west and a frigid east. In January 2019, we had very bitterly cold air over the Midwest, record-breaking. In February 2021, if you're watching this from Texas, the Great Texas Freeze, February 21, just incredible. And then December 2022 was that pre-Christmas frigid chill that just came down. And then January 2025, just this past January, the Gulf Coast snowstorm. So let's just examine some of these examples, and then we'll work our way into the findings to wrap things up. So January 2010, January 1st through the 10th of 2010, this purple coloring here is indicating well below normal upper heights, 18,000 feet. Now, when it gets very below normal, these upper heights, that's associated with very, very cold air. So you have deep upper level low pressure in the purple coloring over the northeastern U.S. You got this high pressure in the yellows and oranges here over the western U.S. So you have upper level ridging, a wavy jet stream, okay, over the western U.S. upper level ridging, and you get a deep upper level trough from the Midwest to the East Coast. That's what happened in January 2010. This cold wave was associated with the negative phase of the NAO as well as the negative phase of the AO. And it was an El Nino winter, the 09-10 winter, but the strongly negative AO and NAO overpowered its effects. Now look at this. This is the AO, the Arctic Oscillation graph, in the winter of 09-10. Look at this drop off from November 29th, and it bottoms out around December 21st, just before Christmas of 2009, and it stays negative, deeply negative, all the way to mid-January. So you're looking at a period of over 30 days where you have a strongly negative Arctic oscillation, which then tends to result in this very wavy weakened polar jet stream. These were the graphic, these other charts here, 500 millibar charts, 18,000 feet, the upper level winds and the upper level pressure systems. This is December 24th, Christmas Eve 2009. So we really start seeing this major upper level ridge. This polar jet stream is weakened and it's wavier. You get a very deep trough in upper lower Texas. By December 28th, the next diagram over here where I have my red laser pointer, we have a little bit of troughing over the coming into Southern California, but you really have a direct fetch of very cold Arctic air from the Arctic area straight down into the mid-Atlantic and the New England area. January 1st, 2010, You still have that troughing, that ridging still over the western U.S., the troughing, the central and the eastern U.S. And then this is January 5th, 2010, a deep, deep trough all the way down to the Gulf of America, all along the Gulf Coast there, and in northern Florida. And then figure 11 over here on the right just shows how entrenched this cold air mass is here within the trough of that weakened polar jet stream. February 2010, another example. Look at the upper level heights in this maroonish color, this orange coloring. That indicates well above normal upper level heights, which is associated with very, very abnormally warm temperatures. The blue coloring indicates anomalously low upper heights, which is associated with unusually cold temperatures. And you can imagine what happens when you get a storm to track up the East Coast multiple times in this February 2010 period. In very cold air, you're going to get a lot of snowfall. So just some highlights from February 2010 when the polar jet stream was weaker and wavier. Several southern states experienced their coldest February on record or within their top 10 coldest. I mean, look at this. The cold went all the way down to Florida. It was the fourth coldest February on record in Florida, fifth coldest February on record in Louisiana, Alabama, Georgia, and Texas, sixth coldest February, Arkansas, seventh coldest February, and then Mississippi and South Carolina, the eighth coldest February. There was record-breaking snowfall to several locations along the Atlantic coastline. For example, let's do some totals here. February 2010, Washington, D.C. Dulles Airport received 46.1 inches of snow, surpassing its previous mark of 34.9 inches. Just phenomenal. Central Park, New York recorded 20.9 inches during the 25-26 February snowstorms. This contributed to its all-time monthly February record of snow, up to 36.9 inches in the Central Park, New York area, just by the simple fact we have this weaker, wavier polar jet stream with anomalously upper high heights and anomalously warm temps over the Arctic and below normal heights and anomalously colder than normal temps, really from the Rockies eastward to the East Coast. February 2015, you can kind of see the graphic here. This is the average temperature departures from NOAA. February 2015, look at this dividing line here around the Rockies. Anywhere east of the Rockies, blue coloring, below normal temperatures. And these are in degrees Fahrenheit here per the legend. Over here to the west of the Rocky Mountains, all the way to the west coast, you're warmer than normal in February 2015. And you can see the jet stream pattern here. They show this on the Weather Channel, but this was a dominant pattern late January to February 2015. Very cold temps. Look how wavy the jet stream is. Look how deep that trough is digging there in the northern Gulf Coast. And you got very cold air contained within that deep trough. And underneath that ridge, you got very warm temperatures across the western U.S. So with February 2015, some highlights here on the right. We had a prolonged intense cold wave covering the eastern U.S. and Canada, characterized by frigid temperatures, significant snowfall as well. This also was caused by the stratospheric polar vortex being displaced, and that reflected down towards the troposphere and changed the polar jet stream configuration to what you see here with the trough in the east. There was a resilient ridge over Alaska, and cold air generally moved over the top of the ridge right on down as far south as the Gulf Coast. And this resulted in a series of broken low temperature records as well as snowfall in February of 2015. Here's an example. This guy is digging out this path of snow in Boston, Massachusetts in February 2015. I mean, this snowbank is about as high as this guy's height, which I'm guesstimating maybe 5'10" right here. So, I mean, 70 inches is 5'10". I mean, that's insane. He's trying to shovel a path here in between these humongous snowbanks. Caribou, Maine in February 2015 experienced its coldest February on record. Buffalo, New York recorded its coldest month on record with an average temperature of just 10.9 degrees Fahrenheit. Even in Virginia, southwestern part of the state, Lynchburg, Virginia set an all-time record low of negative 11 Fahrenheit. Flint, Michigan tied its all-time record low of negative 25. All right, when you're tying all-time record lows in Michigan in winter, you know it's cold. Boston, Massachusetts, 64.8 inches of snow, recording its snowiest month on record. I mean, that's just in February. Can you imagine that? That's just phenomenal. All right, now let's move on to the January 2019 event. You can see here, these were observed low temperatures I'm showing you from January 30th and 31st, 2019. These are low temperatures. These are air temperatures. This doesn't include the wind chill. International Falls, 40 below low temperature, 45 below low temperature. Chicago, 23 below zero, 21 below zero, back-to-back mornings. Des Moines, 20 below and 14 below zero back in January 30th and 31st, 2019. I mean, this is just phenomenal cold. And over here on the bottom right, I'm showing the coldest wind chill values. The wind chills were 65 below zero. That's what it felt like between the effects of the very cold temperatures and the winds across Minnesota. 65 degrees Fahrenheit below, negative 65 Fahrenheit. That's what it felt like outside. 62 degrees Fahrenheit below zero across parts of eastern South Dakota. And 49 degrees below zero Fahrenheit. That's what it felt like the wind chill in Chicago. It's down to like negative 10 in DC for the wind chill, one above zero in Southern Virginia. I mean, my goodness. What happened is there was a change in the polar jet stream, became more wavier and weakened, caused by the southward displacement and weakening of the stratospheric polar vortex over the Great Lakes. So the stratospheric polar vortex weakened, came down over the Great Lakes area in this example. Now, this one was a big one. February 2021, if you live in Texas, you know what I'm talking about. Great Texas freeze. And the 500 millibar height anomalies here in this graphic here on the left, the blue coloring indicating those well below normal upper level heights again at 18,000 feet, which is also supporting record cold temperatures all the way down from northern plains, Midwest, all the way down to the Gulf. Okay, the Gulf Coast area. So you see the coloring here, I kind of labeled that. Now, where you see the red and orange colors, this indicates anomalously above normal heights, and that equates to anomalously warmer than normal temperatures across the Arctic. Look at this ring of ridging over the top across the Arctic, and beneath it you get this just major push of cold Arctic air dislodged from the Arctic down into the lower 48. I mean, this is just so ideal if you like cold air. I mean, you got upper level ridge into the northeast Pacific towards the Gulf of Alaska. You got another anomalous ridge over the Arctic area itself. You got another ridge on the Atlantic side up toward between Greenland and Canada. I mean, this is it. So the stratospheric polar vortex collapsed in middle January of 2021. It weakened the polar jet stream winds, reshaped the jet stream into a wavier pattern with a deep trough into the United States. There was also a strongly negative Arctic oscillation, or AO, which contributed to the cold air outbreak. Oh, that's a theme, isn't it? A strongly negative AO, colder temperatures in the U.S. Yeah, that happens. That allowed Arctic air to spill south into the United States. So Texas experienced the worst consequences of this cold wave with widespread power outages. We're talking about a complete power grid failure. The average temperature across Texas on the 15th of February 2021 was 11.8 degrees Fahrenheit. And every Texas county was under a winter storm warning. Accumulating snow fell as far south as Houston, where they received 1 to 3 inches of snow on the ground. Moving on now to December 2022. These are the temperature anomalies, the purple coloring indicating the 25 to 30 degrees Fahrenheit below normal in December 2022. With this particular purple coloring from the northern plains down to the Midwest into the Ohio Valley, deep south, worked its way all the way to the East Coast. Just phenomenal. This was for the Christmas Eve of 2022 here. It was a cold wave associated with a weakened polar jet stream and a negative AO index. There it is again. Negative Arctic Oscillation Index, weakened polar jet stream. This was actually a La Nina winter, along with extensive snow cover from the previous month, may have amplified the cold wave. So the combination of La Nina with extensive snow cover could have really helped this cold, very frigid air buildup over the colder snow-covered surface up into Canada and Siberia. Now, all U.S. states from Colorado to the eastern seaboard were impacted. There were blizzard conditions affecting parts of the Midwest, Great Lakes region, as well as eastern Canada. This was that case where excuse me, Buffalo, New York received over 56 inches of snow over just 5 days. The lake effect snow machine was cranking at high effect. And then finally, January of 2025, look at this. A weaker, wavier polar jet stream. Pink colors here along the Gulf Coast indicate winter storm warnings. This is just unbelievable. South Texas, Houston again, southern Louisiana, including New Orleans, Biloxi, Gulfport, Mobile, Pensacola, Tallahassee is over here. Panama City is in a winter storm warning. This was phenomenal. This was a notable cold wave in January of 2025, affected the south and southeast, bringing unusually cold temperatures. There was a large trough or a dip in the polar jet stream again, which extended from the Great Lakes to the Gulf Coast. And we had a historic snowstorm here along the Gulf Coast on the 21st of January, 2025. Here are your totals. Mobile, Alabama, 7.5 inches of snow. Pensacola, 8.9 inches. New Orleans, 8 inches. And Baton Rouge, 7.6 inches. I mean, whoever would have thought on the 21st of January, 2025, these winter storm warnings were going to be up, down, all the way down the Gulf Coast area. Just phenomenal. These deeper blue colors, by the way, indicate cold weather advisories of some sort. So finally, to end this video here, here are the findings. I did a lot of digging into all the references I showed you earlier. A warming Arctic may affect the tropospheric polar jet stream, the strength of it, as well as its position. A weaker jet stream could lead to longer periods of anomalous weather patterns, depending on your location in relation to that jet stream. Are you located beneath a ridge, or are you located within that trough? Different weather is going to occur as a result of that. In the trough, you're going to find the coldest temperatures and the stormiest conditions. In the ridge, you'll find the warmest temperatures and very dry conditions. You can get droughts, floods, this anomalous cold and warmth, all possible during a weakened, wavier polar jet stream. The weakened stratospheric polar vortex contributes to the weakening polar jet stream, ultimately reorientating the jet stream's position. And it's still unknown if Arctic amplification, the warming of the Arctic itself, is the sole contributor to a weakened polar jet stream, or if this is just a natural variability of the jet stream in general. Is it more cyclical in nature? Now, I will say from the years, now I'm going to show you that here in a minute. Okay, I'm getting ahead of myself. All right, so a decreased latitudinal temperature gradient in winter acts to weaken the polar jet stream, creating more waviness to it. On the other hand, you got all these researchers saying, hey, we're getting a weakened, wavier polar jet stream because of this Arctic amplification, where the Arctic is warming 2 to 4 times faster than the rest of the planet. Makes a lot of sense. However, research conducted by Shaliff, Gurani, and Osterberg show the jet stream's changes may be due to more of natural variability. They did research and looked at this, and they went back beyond the satellite era, but all the way back to 1900. And they believe that these polar jet stream changes are due more to natural variability by Arctic amplification. So, for example, in their research, they identified that there was a warming hole period across the southeastern U.S. during the winter from 1958 to 1988, which resulted in deep troughs, increased jet waviness period from 58 to 1988. And that resulted in abnormally colder winter temperatures. We're talking 2 degrees Fahrenheit below normal across the eastern U.S. This is the graph I pulled right from their research paper. And so we have waviness going back to the year 1900 through 2020. Whenever this line goes up, that's increased waviness, a weakened polar jet stream. When it goes down, it's a decreased waviness and a stronger polar jet stream. So it goes up, the polar jet stream is stronger. It goes down, it is weaker. Or I'm sorry, if it goes up, it is weaker. When it goes down, it is stronger. Sorry, I'm getting mixed up here. But anyway, there was a warming hole period. They note that in this graphic where there was increased waviness. You see these peaks here, especially in the 1960s. We had a drop-off in portions of the 1970s, but then it came back again into the 80s, early 80s. really strong, increased waviness, which indicates a weakened polar jet stream. Okay. So there is opposition, and there's still a lot more research to be done in this area. All right, that wraps things up here with my video. I know it was really long. I really packed in a lot of information in this video for you. But in general, this was the changing polar jet stream during Arctic amplification. Is the polar jet stream becoming wavier? Is the polar jet stream becoming more frequently weaker? Are we seeing deeper troughs and stronger, more amplified ridges into high latitudes, right? Deeper troughs into the mid latitudes. Are we seeing more extreme cold temperatures? Many people have done great research out there, and I encourage you to go out there and do the same. Just Google the topic that I have here on the title slide. Just Google this, and you'll get a whole bunch of great research papers out there. Just great work all around. So, all right, that wraps things up this evening. I certainly hope you're staying cool. And until next time, take care and God bless everyone.